Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be finishing up our discussion of the kinetic gas model. So last time we were able to derive the ideal gas law through the use of determining the velocity of a gas and how that can exert pressure on its surroundings. Today, however, we're going to be looking at a little bit of an extra nuance feature. We're finally going to talk about how gases interact with each other. And this is important because it's going to actually drive a couple of important physical phenomena like the diffusion of gases. So let's go ahead and dive right in. So last time, we were able to figure out the velocity of gases in how they were hitting a wall. But the problem is when I'm actually working with gases, what I often much more care about is how the gases will hit each other. So what's going to be the relative velocity of two gas molecules to each other? As this is going to dictate both how hard they hit, but also how frequently they interact. So the problem is that there's a whole realm of ways that they can interact. So for example, if we could imagine two gas molecules moving in the same direction, in this case, what you'd have is almost a zero velocity impact that goes on for a long time, as they're kind of just riding their tail like having somebody tailgate you. And on the other extreme, we can have two gas molecules that hits head on, at which point the collision velocity is about 2v. As again, you're feeling the full force of both velocities impacting each other directly. So this is like a head-on car collision. However, we also have the realm of everything in between. So as a result, we expect that the most common uh, type of frequency would be two gas molecules hitting each other at a right angle. Some are going to hit a little bit less than a right angle, some a little bit more. In each case, the average velocity of collision will end up to this right angle collision. Then we can use the Pythagorean theorem to show, okay, if I've got two velocities impacting, the degree in which they're hitting each other is going to be about 30% greater than the velocity, or the velocity times square root of 2. So it turns out this is going to be the average relative velocity. So if you know the average velocity of molecules, frequently here we're going to use the RMS, then we'll multiply that by square root of 2 to get the relative velocity. Now, why does this matter? Because if I know how fast the molecules are moving, I can figure out how many molecules it will collide with. So we can imagine this molecule traveling through space, curving out a sphere of interaction. So if my gas molecule has a diameter of d, and all of the other gas molecules are of, again, the same size, then it will go ahead and collide with any other gas with a radius of d. Because again, if it's shorter than that, the two radii overlap. If it's greater, then the two radii do not overlap, and that's going to be a clear miss. So this tells us the cross-sectional area that a gas molecule will carve out. And since the radius is d, that means this cross-sectional area is going to be pi times the diameter of our gas squared. So we're going to carve out an area along the trajectory of this molecule. Now the question is, okay, now how many gas molecules am I going to hit along the way? Well, not too surprisingly, that's going to depend on the velocity. Because the faster you move, the more molecules you'll hit. The slower you move, the less molecules. So the volume is just going to be that cross-sectional area times the relative velocity times the time of interest. So the longer the time of interest, the more molecules we hit. So now using this, we can figure out the number of collisions uh, by multiplying the volume that gas goes through by the molecular density. So this is simply just going to be the number of gas molecules per a given volume. And then we can multiply that by that volume of interaction. And this will give us the number of collisions that a gas has for time t. So if I want to know how many times a gas molecule collide in 1 minute, we put 1 minute in here. We'll put the relative velocity in, usually something like meters per minute, the cross-sectional area, the volume, and the number of molecules for that volume. So then what we can do is we can rearrange this by looking at the number of, we can go ahead and combine all of these features by saying, hey, I can use the ideal gas law and say that the number of molecules times the velocity is going to be the same thing as the pressure times the Boltzmann constant over the temperature. Because again, just literally inserting in the ideal gas law. And then going ahead and combining this, we can go ahead and figure out the number of collisions based on the size of the molecule. We're using the pressure as a measure of concentration, the temperature, which is readily determined, and again, that time of interest. Longer time, more collisions. Hotter the system, the fewer collisions, because again, this will play some games with the density. But note that we do have this interesting relationship in between the relative velocity and the temperature. So what we can then do is rearrange this to honestly a more useful thing, which is the frequency of collisions. So in this case, we divide both sides by t, and we get the number of collisions per unit time. So frequently, the frequency of collisions will often be something like the collisions per second. So then we can plug in our relative velocity, which again, we can derive from the root mean squared velocity we expressed last time. The temperature, the pressure, and then this cross-sectional area depends upon the identity of the gas. Larger gas, more collisions. Smaller gas, fewer collisions. So one of the reasons why this is often useful is that we can use this idea of the frequency of collisions to figure out how far a given gas molecule can travel in between a collision. Now, this is often important when you're trying to figure out things like the rate of reactions in gases, as this will often be dictated by how likely gases collide into each other. So we often are going to look at this using something called the mean free path. So this is expressed as lambda. And this is the distance that a gas molecule can travel without hitting another gas molecule. So this can be simply given as the speed of the gas divided by the frequency of collisions. So in units, this will often be meters per second divided by per second, giving us a simple distance. Now, we can reframe this in terms of measurable properties, because again, none of these are directly measurable. So here we have our relative velocity, and then we can plug in our equation for z. Now, at this point, remember that the frequency of collisions includes the relative velocity itself. So here we will expect these two terms to directly cancel out, and we're left with a much more useful property than something like the frequency of collision, because now I know exactly how far a gas molecule will travel based on the Boltzmann constant, which is a constant, temperature and pressure, which are readily measurable, and the cross-sectional area, which is going to be unique to the gas of interest. So using this, we can go ahead and figure out this mean free path is going to be highly related to something like something called the rate of effusion, which is more commonly known as diffusion. Effusion is literally just how fast a gas diffuses into an environment. So it's a gas-specific environment. And the idea here is that as a gas is traveling through space, it goes through something called a random walk. It will travel some distance, collide with a molecule, go off into a different direction, collide again, go off in a different direction. And as it progresses, this is called a Brownian motion, as the particle is traveling randomly through the environment. Now, the important thing here is that the longer the mean free path, the less time in between these collisions, and thus, even including random motion, the molecule is more likely to travel further than if it didn't collide at all. So as we increase this mean free path, We can do this by increasing the energy of the system by heating it up, or reducing the concentration by lowering the pressure, or by using a smaller gas. In any of these cases, we'd expect this distance traveled by a gas molecule to increase. Now, this is often important if you're trying to examine something like toxins. So if I release a toxic gas, it will tend to concentrate more in spaces with high pressures because it's going to collide with more things, or low temperatures because it just doesn't have the same energy. And this is also the reason why a lot of toxic molecules are often a little heavier. They travel less far and they can tend to build up. So again, we get some really useful features just out of this idea of random movement. Conversely, yeah, so again, if you've got something that's very slow, so very cold and large, it won't travel quite as far, and this can cause some real issues in any number of environments. So that brings us to the end of looking at our kinetic gases. So next time, we're going to go ahead, take a step back, and look at our ideal gas law and how we can really put it to use and how it acts as a fundamental equation for chemistry. Until then, take care.